Okay, so our first speaker this morning is Dr. Howell, who is professor of voice and pedagogy at the New England Conservatory. He studies the special psychoacoustics of the singing voice. He's performed on 5 continents as a soloist and is a member of the Grammy Award-winning ensemble Chanticleer. Thank you.
Good morning. Hi. Thank you very much. I want to say hello, good morning to everybody. I know 9 o'clock in the morning is early to come and listen to recordings of singers, so I'm grateful for that. This is also my first time coming to the Society for Music, Perception, and Cognition, and I've had a great time. So I want to thank all of you who are helping to make that possible. The title of my talk is In Search of the Soprano Singer's Formant, a Perceptual Approach. This is a project that I've been working on for a few years in conjunction with one of my graduate students, Rebecca Worthington. The plan for this morning is I want to introduce both the singer's formant and also issues with the way that we teach about the singer's formant. I'm going to introduce a simple model for singing voice psychoacoustics that we use at the New England Conservatory, and then I'm going to introduce and explore a pilot study that we recently did. Just to give you a little background, I'm first and foremost a voice teacher and a classroom teacher of voice pedagogy, voice science, and voice history. So when I say voice pedagogy, really what I mean is fact-based voice pedagogy. Fact-based voice pedagogy, at its core, is all interdisciplinary. So what we'll do is we'll set up these silos, and each silo might be a different chapter in a voice pedagogy book. So we'll say singing voice and anatomy and physiology. We've been doing that very well since at least the mid-19th century. Singing voice and language and phonetics, that tradition is almost as old. Some more recent ones are singing voice and acoustics, and singing voice and kinesthetics. I think what's missing is singing voice and psychoacoustics, and it's fascinating that it's missing, because if you start to understand the color present in any sound in terms of the limitations of the ear itself, then you're just confronted with the fact that the hearing mechanism is a co-creator in the sound of any human's voice. So some singing-specific issues when we look at the voice psychoacoustically. We frequently sing at higher frequency fundamentals than you find in speech, although the bulk of the research is about the speaking voice. We have the potential for near continuous state sounds. I know no sound the human voice can make is actually a continuous state, but we'll have long tones with sustained vowels. We'll have a single vowel that is set melismatically, so that's to say same vowel sound generally that's set over several pitches in a line. And it really calls into attention, calls into focus a difference between audition and cognition for the human voice. So when you listen to a flute playing, for example, you don't struggle to layer linguistic meaning onto the sound. You're comfortable confronting that raw objective timbre of the flute. When we listen to somebody sing, there is circuitry in the brain that instantly starts decoding the words that they're singing. So I think for most of us, it's a lot easier to pay attention to the words and pay less attention to the actual objective inherent timbres that are present in the voice. And then the last little bit of background that I think is important is just to locate my perspective is I'm less interested in what the human ear generally across a broad population can hear. I'm very interested in training elite listeners. So it's important to understand that singers and singing teachers are not just elite voice users, they're elite listeners. If you want to pay the biggest compliment that you can to a colleague of yours who is a voice teacher, tell them that they've got big ears. That's how we compliment one another.
Big ears?
Big ears. You listen with big ears. That's what we say. So for me, that means that the better the labels we give people who listen to singers, the better their perceptual labels are, the more detail that they're going to be able to bring to the experience of listening to a singer, and then the better they'll be able to diagnose faults and sort of prescribe corrections. So the singer's formant, what is it? Within the present day literature, we give it a couple characteristics. It is a high amplitude band of energy. We describe it as being rough and bright. Typically falls between about 2.3 and 3.8 kilohertz, depends on the singer. And in the literature, it's generally listed as exclusive to the male classical voice, sometimes present in the female voice below about the pitch D5. And it sounds like this. This is an excerpt of Franco Corelli. This is from A te Okada, the aria from Bellini's I Puritani. if we just filter the portion of the sound that is his singer's formant, it sounds like that. So this has been described since, essentially Helmholtz references it in his writings, that there's a tinkling bell-like quality in some voices that you'll hear. But we've been talking about it in modern terms at least since Bartholomew, who was a professor of voice at the Peabody Institute in Baltimore. And in the mid-1930s, he says that cultivated voices have a higher ringing formant that is present, and in fact that you can judge the quality of a voice by how loud this is. He may be the first person who inserted the thought that it's really only present in male cultivated voices and it disappears as female voices rise in pitch. More recently, it received its actual name, singing formant, or what we call singer's formant, by Johann Sundberg in the 1970s. And then in 2003, he suggests we should actually call it the singer's formant cluster. The advantage to this term is that it describes both the phenomenon, the bright ringing quality, and it also describes the means of production. So if you think of the resonances of the vocal tract, the way that we get that clustering of energy is by causing the third, fourth, and fifth vocal tract resonance. The vocal tract just has pitched resonances. We bring them close in proximity. We cluster them, and they mutually boost and reinforce one another. Why this might be an advantage? Well, this is a graph, amplitude low to high, frequency low to high. This is sort of a general spectral power representation of what an orchestra does. This is the frequency range they tend to occupy. If you average large recordings, long recordings, this is a voice with a singer's formant. So you see that they have a lot of energy in a frequency range that orchestral instruments do not. And so the thought is that they're competing for the listener's attention in the most advantageous part of the spectrum possible. The problem, though, is that this description does not fall in line with the experience of many classical singers. And we started down this road of inquiry because my student, Rebecca Worthington, in my class, when I taught the singer's formant out of the textbooks, her response was, that's not me. That's not my experience of singing, because when she sings, she has a bright, ringing, buzzy quality that is omnipresent in her voice. So we decided to investigate this with a model we use at NEC. And we look at the voice psychoacoustically through the intersection of three properties: pitch, auditory roughness, and a property that I call absolute spectral tone color. Now, I wish I had a lot of time to go into absolute spectral tone color today. It is a way that we characterize and define labels along the scale of brightness. I'll play a little example of that in a minute. So the way that the model works is, if you have a generic harmonic series, first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic, you can generally assign a quality of purity, which is to say there's no auditory roughness to the lowest five harmonics. And as you get from the fifth harmonic and higher, the sound becomes progressively rougher and rougher. Now, I know there are exceptions for very low fundamental frequencies, and also it depends on how pristine the signal-to-noise ratio is in terms of the harmonics themselves. But if we accept this as a very simplified general way to think about it, I would be grateful. Onto this, we can overlay the resolution of harmonics into the pitch. So that's to say, generally, the lowest 8 harmonics are going to be folded into our percept of the pitch. And from the 9th harmonic and higher, it's not a light switch, but they progressively become less and less relevant to our perception of the pitch. So that actually defines 3 broad areas. We have harmonic 1 through 5 is pure and resolved. Harmonic 5 through 8 or 9 is rough and resolved. And from the 9th harmonic and higher, they are rougher and progressively more unresolved. If we overlay an actual voice onto this, so now we have piano keyboard, these harmonics are have actual frequency. What we can see is it matters what pitch you're singing. So in this case, we have our first and second formant, which are the vowel characterizing formants, and then we have the singing formant here. And we see in this voice that the singing formant will be rougher and progressively more unresolved. If we jump forward to a soprano singing a high G instead, if we keep the same frequency window, what we find is that there's no evidence that she is creating any harmonics that would do anything but a pure and resolved sound. Now, just to tease out this absolute spectral tone color question briefly, if we look at the pitch E4, we see that it has an absolute spectral tone color. It's similar to the vowel oo. This is the pitch E4. I chose chose this pitch because the lowest vocal tract resonance for these two vowels in this singer's voice essentially is the pitch E4. So the first harmonic is going to have equal loudness the entire time. So if we listen just to that first harmonic, where's the E? This is the question, right? So because it has the same frequency the entire time, it exhibits the same tone color the entire time. And in fact, you can come to understand the E vowel without that first harmonic. Now fade it back in, and I want your label to be, I'm going to listen for the OO, okay? So if we go back to the Corelli, if we remember the high C that he sang, his singer's formant is harmonics 5, 6, and 7. We would say those are in the tone color range that is like E or even into very bright E sound. They are rough and they are resolved. Is rough, resolved, and an E to bright E tone color. These are the perceptual parameters that define his singer's formant. So then the question is, can we just find this in a classical female singer's voice? Just look for it perceptually rather than look for it in the frequency band where you find it in the male voice. And the crazy thing is, as soon as we started looking for it on commercial recordings, it is all over the place. It is hard to get away from. Perhaps if you have a very lofty, quiet high note, it's less present. But anybody who is singing fully, you will find this so long as you look for it. So then we set up a pilot study because we wanted to control whatever variables might have been present in all of these commercial recordings. Maybe the engineer is given a little tweak because they know it'll make it sound more silvery. So what we did is we took 4 graduate level full or heavy lyric soprano voices from the New England Conservatory. We recorded in a concert hall in Jordan Hall in Boston, which is a great space. We gave them 3 singing tasks. They had to sing an excerpt from the repertory so they would remind themselves that they were actually singing. They sang an ascending scale from A-flat 4 to A-flat 5 on the vowel of their choice. Interestingly, everybody basically picked the E vowel up to about E-flat 5 and then the A vowel from F5 to the A-flat 5. And then they sang a descending scale from the A-flat 4 to the D-flat 5. Everything I'm going to show you today is from the 3 highest notes of that ascending scale. We used 2 microphones, one about 6 inches from the singer's mouth, slightly off axis to try to decrease any breath noise if possible, and the other one about 25 feet away in the hall, raised up to their head level, because we were trying to tease out whether there was some sort of acoustic trickery that was going on, and you would hear it up close but not in the space, or hear it in the space but not up close, and they were negligible. The only real differences were reverberation, as you might expect. And prior to each sample, we had the singers stand, at the edge of the stage, and we literally reminded them that there was an imaginary symphony orchestra behind them to try to just put them in performance mode so they would sing as fully as they would in performance. Now these are the results. These are, each one of these lines represents one of the singers. This is a power spectrum view, logarithmic display of frequency. This is amplitude from low amplitude to high amplitude, and this line is placed at about 4,000 hertz. So this is essentially the top of where we might expect to see the singer's formant in a male voice. And what we see is there is indeed a good deal of energy below 4,000 hertz. Typically, these harmonics for the pitches F5, G5, and A-flat 5, this is long-term average spectrum of those pitches, those harmonics are at the bottom end of their harmonic series, and so as a result of that, there's no roughness, there's no buzziness, it's a very pure resolved sound. However, there is a ton of information up here. There's a ton of harmonic information in the space above 4,000 hertz. So let's listen to it. I'm going to play you samples from 2 of the singers, just because of time. First, I will play you F5, G5, A-flat 5 from one of the singers. And because the effect is more dramatic the higher the pitch is, I'm going to start with the A-flat 5. Now I've deleted everything above the 5th harmonic. I've deleted all the information above that 4,000 hertz line. It sounds like this. So we have vowel, and we have purity of tone. There is some breath noise in there, so there's some small amount of roughness as well. Now if we listen to the remainder of the envelope, it sounds like this. which I would characterize as rough, bright E, and actually in this case it also resolves into the pitch, although it's a little tough because we all just heard the A flat 5. So then the question is, and this is how we do ear training protocols at the conservatory, if I add that rough, bright quality back in, do you notice it? So we're going to start with the low part of the spectrum and then fade the bright part back in. From a cognition point of view, you don't need that to understand that's an ah-like vowel. From an audition point of view, it is actually a significant contributor to the timbre. And if we're talking about singers who make timbre choices for artistic reasons, who make timbre choices for workplace requirements because you need your sound to carry a certain distance, and high frequency harmonics are far more directional than low frequency harmonics. So as long as you're pointing at the audience, if you have high frequency sound, you're more likely to be heard by audience members. Now, just so you hear a little bit of variability, because there is variability, this is one of the other singers. This is her entire voice. This is lowest 5 harmonics. Her bright area is actually noticeably brighter. And then when we fade it back in, so then the conclusions that we might be able to draw from this, first of all, defining the singer's formant perceptually rather than by its method of production is actually freeing for both male and female voice perception. Because if we go back to the Crelli ever so quickly, this is his singer's formant band on the C5. That is bright, piercing, very E-like in quality. These are all his harmonics above it. Like there's information there. There's information there that is relevant to the perception of the singer. If we take them away, like it's a quality that adds to our perception of the voice having brightness. So if we're saying every bright sound we hear in a classical tenor voice is somehow relegated to this narrow singer's formant frequency band, we're actually selling ourselves short for the guys too. I think we need to at least accept that it's possible that females singing in heavier Fox may exhibit a singer's formant-like quality. We just need to look for it in higher frequency ranges than we look for it in men. And then lastly, and just generally, I think the more specific our labels can be, the more likely we are to be able to train people to hear these qualities. So that's it. Thank you very much. And I'd be happy to take any questions. Yes?
When you faded it back in, that was back to the original power.
Isn't it shocking?
It's really shocking.
Yeah.
It sounds way overdone when you do that.
Isn't it's really weird? Yep.
Yeah, so I guess it wasn't a question, it's a comment.
I think that a lot of pianists think that the sound that they should hear is the sound they see on the paper or what's defined by the keys or the finger. And singers don't do that. So when pianists work with singers, their tone is unbelievably improved simply because of what happens in their ears.
Yeah, you have to listen up and down with the singer.
And you have to have that flexibility that the voice imparts, which of course the piano does. People think the piano doesn't invite it. That's
Right.
why I think you have to take your big ears.
Well, and it's very interesting too. Any of you who are either in school right now taking any music theory courses or teach them, I would encourage you, if you give a student a piece of music to analyze, give them a spectrogram of it. Because forte with an accent actually changes the overall envelope, right? It's going to put high frequency energy in a piano sound that is not present in a piano. A quiet sound on a piano is not the same thing as a loud sound on a piano, but just diminished in intensity. The entire spectral envelope changes. Yeah.
So this is not anywhere near my area of expertise, and I really don't know that much about the singer's formant and spectral stuff in general, but I'm just wondering why, if you can talk a little bit about why you might think that there's been this limitation to thinking that the singer's formant is only present in men, and why they've been sort of like had this sort of like, I don't want to say narrow-minded, but this sort of like restricted sort of view of that it only exists in this particular band and therefore it can't exist in the female voice. And if you by changing your definition, if this is how it's typically defined, then it seems rather obvious. It should seem rather obvious that it would exist. I'm just wondering if you...
My short glib answer is that everybody doing the research studies, they were all men. And I actually think there's a lot to that. My less glib answer is that if you look at the silo that is voice pedagogy and acoustics, we take all of our basic research from the research that came out of Bell Labs that brought us the telephone.
Right.
And if you're talking about speaking voice comprehension, then you're really looking at a frequency band between 400 hertz and 3,400 hertz or so. I don't know if any of you, a couple of you in this room might be old enough to have actually talked on a copper wire telephone. And it's a very distinct sound because of the information that you're cutting out. But the primary research from those studies told us that vowel comprehension can be captured as long as we have a frequency band wide enough to get the first and the second vocal tract resonance, and to a certain extent the third vocal tract resonance. And so if you're just looking at that frequency range, that doesn't take you higher than 4,000 hertz anyway. I think it's just bias of omission. Like I don't think people meant to do this. But if you want to go out and buy a commercial package spectrogram that's used in voice pedagogy programs across the United States, the default setting is going to be up to 5,000 hertz. If you don't go in and tinker with it, you're never going to see the energy in the female voice in the first place. And because our labels dictate what we listen for, like we don't actually have a good verb for it. Like if we know where to look, we can see things. If we know where to listen, we'll hear things. But it's just a matter of we never see it because of the software itself. Yeah.
Quick follow-up. What was the range for this performance? So starting at 5,000 hertz up to 7?
Yeah, so I default to about 15,000 hertz on my spectrograms, not because it's always relevant, but because my own bias is that's the limit of my hearing right now. So, so I can't really hear higher than 15,000 hertz. Almost all relevant energy in the female classical voice that I'm referencing here doesn't go much higher than 9,000 or 10,000 hertz anyway. I just want to make sure I catch stuff that will surprise me. Yeah. Any other questions? Yeah.
I just want to point out that I considered it a huge leap in the direction of civilization when the music school I was affiliated with for a long time had special ear training for singers.
Mm-hmm.
That was such a big deal. I couldn't imagine that they expected singers to hear as pianists hear, for example. Why should they? They don't. So anything that can open the definition of that psychoacoustical phenomenon is good for all of us.
I agree. I totally agree.
Very important.
And as a voice teacher, we have this term we call functional listening, which is to say just based on the sound, rather than keying into some sense of like empathy for the singer's body, can you just tell by the qualities present in the sound what physiological choices they're making? And it really helps, it opens a window into what we call voice registration, which is how you get from to something better and more beautiful, rather than a broken voice, you have an integrated voice. So that's again my bias that's not beautiful. But if anybody is interested in reading more about this, I do. That's my bibliography. But I will say, if you find me on academia.edu, my dissertation dives into this in great depth, and I also have a recent article from Voice Prints that dives into the model that I presented today. Any other questions? Thanks for the chance to present. Appreciate it.